Now, we've been talking about the ratio test, and we found that it's very useful in determining whether or not a series converges in a lot of cases. But what I want to look at now is the root test, which really just follows immediately from what we've observed with the ratio test. So here, let's suppose we've got a series here, and I want to look at this limit, the limit of the nth root of the absolute value of this thing inside here. So let's just, this seems like a nonsensical thing to do, but let's see what the nth root, the limit of the nth root of the absolute value of that inside is. Well, let's suppose that this is less than r, just some r, and let's further suppose that r is less than 1. Okay? Let's suppose that happens. Well, then that means that for some big N, of course, greater than 0, we have this. We have that the nth root of the absolute value is less than r. Okay? Just because that's what the limit says, right? So we know that if you go out far enough, you're going to have this situation, and this is for all n bigger than big N. Okay, for all little n bigger than big N. Okay, so if you go out far enough, you have that situation. Well, that means that the absolute value of a sub n is less than r to the n. So if you go out far enough, you have that situation. Okay. So the terms of these terms right here are going to be smaller than these. So in other words, notice we've got a couple of series here. We've got this series. Let's think about this. Let's do the absolute value. And we've got this series. Okay. We've got these two series. Now I started off without the absolute value there, but I've now got the absolute value. And remember, if the series converges, if it converges with the absolute value, in other words, if it converges absolutely, it will converge without the absolute value. So now let's compare these two. We know that this one right here is bigger than this one. Okay. The terms of this one are going to be bigger than the terms of this one if you go out past big N. Now, if this one here converges, then this one here converges. And this one here converges because remember, it's a convergent geometric series where R, the common ratio here, is less than 1. So it converges. So this is the root test. So what we're saying is we kind of use the same argument to show this root test that we use with the ratio test. In other words, here's what we're going to say. We're going to say this. The limit, now notice we had this stipulation right here that r is less than 1. In other words, that led us to say, okay, this is a convergent geometric series. Now, if r was bigger than 1, this would diverge. Okay, this one would diverge because that's the way geometric series are. If the common ratio is bigger than 1, diverges. Less than 1, converges. Now, so here's what we have. We're going to have the limit as n goes to infinity of the nth root absolute value a sub n. Now, if this is less than 1, we have convergence. Okay. On the other hand, if it's bigger than 1, it diverges. And if it's equal to 1, the test doesn't apply. We can't determine anything from it. But you notice this is just, it's really the ratio test. Okay. I mean, the same argument that we apply for the ratio test, we apply to this one. So it's kind of a natural extension. So let's look at a couple of examples of how we would use the root test. Let's suppose that we've got this series. We've got n equals 1 to infinity. Let's say 1 over 2 to the n. Okay. Now, the thing is, we don't really have to use the root test for this one because, this is just a geometric series. It might be helpful to us if we wrote it this way. But you can see that's just a geometric series. But this illustrates how we can use the root test. So we have the limit as n goes to infinity, the nth root of 1/2 to the n, and I don't have to have the absolute value there. But notice that that is just the limit as n goes to infinity of 1/2, which is 1/2. So yes, it converges by the root test. So you can see some of these problems, the root tests really make it easy. Of course, we could just look at this one and say that converges by geometric series. Now let's look at another one. Let's suppose that we've got n equals 1 to infinity of n over 2n plus 1 to the nth power. Okay. Okay. Now you can see, this one is going to be perfect for the nth root test because notice we've got the limit and we've got the nth root of n over 2n plus 1 to the nth power. Well, you can see the nth root and that nth power, they're going to get rid of each other. So we've got the limit as n goes to infinity. Forgot to put that here. Guess we don't really need it. We know what we're doing. So this is 2n plus 1. Now, this is really a basic limit, right? Ratio of the leading coefficients, that's just going to be 1/2. That's less than 1, so it converges. Now remember, I didn't say it up here, but this is less than 1. That's how we know it converges. Okay. So these are two examples of how we can use the root test. And a lot of times, if we're working with the ratio test, the using the root test form of it is a lot easier.